This is Theorem 9-16. And before I go ahead and describe what the theorem says, the one thing that I will point out is that we start with a point somewhere outside our circle, and from there we go ahead and draw a tangent line to the circle and one secant line. So we have these 4 different points. So before I show what the theorem says, let's go ahead and approach this same theorem as we have done the other ones. So I'll go ahead and describe a relationship between those different segments by creating some triangles. So the first one that I'll create will be by connecting A to D. So I'll end up with this triangle, DAB, and then I will have a second triangle if I connect A to C. So I am going to be working with this larger triangle ADB and the smaller triangle ACB. Again, they're not equal, they're not congruent to each other, but I'll go ahead and demonstrate that there is a relationship between those segments because those 2 triangles are similar to each other. Okay, so let's go ahead and point out what angles are congruent between those 2 different triangles. So the first one would be angle B. Okay, angle B will be the same for both of those triangles because that is going to be a reflexive angle. Now the next angle that I'll show that is congruent between the 2 triangles. I'm going to start over here with the measure of angle A. The measure of angle A, that is related to half the measure of its intercepted arc. So that means that that measure will be 1/2 the measure of arc AC. Similarly, I have that this angle over here, D, it is inscribed. So the measure of angle D, by definition, that's going to be half the measure of its intercepted arc, which happens to be also AC. So 1/2 the measure of AC. So we have the 2 pairs of angles that are congruent. So by angle-angle similarity, once again, we're going to be able to say that those 2 triangles are similar. Now, I'm going to go ahead and show the other markings so that we can go ahead and correctly identify the names of those 2 triangles. And actually, let me just go ahead and fix something here. Okay, I only want 1 arc mark there because that angle is different from the other 2 that I have. Now, taking a look at the larger triangle, okay, so I'll have that angle A from that large triangle. So that is going to be my 3rd angle. And then for this smaller triangle, ABC, then that's going to be corresponding to this angle over here. So I'll go ahead and name those 2 triangles. So starting with the larger one, I have, let's go ahead and follow the markings 1, 2, and then 3. So I'll go ahead and call it BDA. So we're saying that this triangle is similar to triangle, and let's do the same thing for the smaller one. 1, 2, and 3 markings. So BAC. Now that we have the correct name for the 2 triangles, let's go ahead and use the definition of similar figures. So come up with the proportion. So let's start with this segment over here, and I am going to be working with the larger triangle. So this segment is from the larger triangle, so AB. That needs to be compared to the corresponding side on the smaller triangle. Now, this might be confusing, and that's why it is important that we have the names correctly so that I can just go ahead and take a look at, well, I was using the first and the 3rd letter from the larger triangle. So I should be comparing that to this side, whose endpoints are the 1st and the 3rd letter over here, the 3rd point. So BC. That should be equal to. Now let's choose one other side from the larger triangle. I'll choose this longest side that I have. So BD. So BD, that corresponds to the first 2 letters. So I'll go ahead and compare that to the first 2 letters of my second triangle. So BA. We go ahead and do the cross multiplication. So we're going to have AB times BA. this is going to be equal to BC times BD. What I want you to notice here on the left side of this equation is that AB times BA, that's basically AB times itself. Okay, we can always rearrange those letters because they are the very same segment. Okay, AB is this segment, BA is the very same segment. So I'm just going to go ahead and change this slightly because we are in reality saying AB times AB. Or if we wanted to change it to BA times BA, it doesn't matter. But the main thing here is that I have AB squared, and that's equal to BC times BD. Okay, so we have this relationship. Now let's go ahead and interpret what this means. So the theorem says, if a tangent segment and a secant segment are drawn to a circle from an exterior point, then the square of the measure of the tangent segment, okay, the measure of the tangent segment, sorry, I forgot the square, okay, the square of the measure of the tangent segment, okay, so we're working with the square of the tangent segment, okay, AB is the tangent segment, then that is equal to the product of the measures of the secant segment. So the secant segment is going to be BD, DB, whichever way we name it, times the external secant segment. So in that case, the part of the secant that's in the exterior of the circle, so BC, and that's what we have here. Okay, the square of the measure of the tangent segment is equal to the product between the secant segment and its external secant segment.